Siluria Technologies is a company founded in 2008 that uses natural gas to directly produce ethylene. It uses natural gas and methane, one of the most abundant compounds on Earth, to produce fuel and chemicals with an innovative unit operation, the OCM, that will be discussed later. Siluria takes advantage of the abundance of natural gas. It is predicted that U.S. natural gas production will increase 56% by 2040. Most of the natural gas produced today is used for heat or raw materials, and with a lot of the world's natural gas being logistically trapped by politics, utilizing the most natural gas for better purposes is the goal of Siluria. Methane is also abundant as a release of agriculture operations, and its capture and use will be beneficial as it is a greenhouse gas, and it being released into the atmosphere is very bad for the environment. With headquarters in San Francisco, 2 plants in Menlo Park and Hayward, and the demo plant in Texas, Siluria Technologies is on the rise. The ethylene industry is huge, as ethylene is the most widely used petrochemical for a market of $200 billion a year. Today, ethylene is made by thermally cracking large amounts of ethane or naphtha, which is costly, long, ineffective, and requires extremely high temperatures. But Siluria uses a direct catalytic exothermic reaction with natural gas to produce ethylene. To produce ethylene in a more abundant and efficient way, Siluria had to produce and try out numerous catalysts, about 70,000 in a couple years, while old strategies could only test one a month, and has found one or a group of catalysts that has produced desirable results. Siluria has produced a revolutionary technology that has created much excitement in the industry, and its economic advantages are over hundreds of millions of dollars per year compared to cracking. Future applications include world-scale ethylene and power, and retrofitting refineries to better deal with natural gas.
This is the process flow diagram for the oxidative coupling of oxygen, ethane, and methane to produce ethylene at a very high purity. The first step in this process is to take oxygen gas, ethane, and methane and react it at 1000 degrees Fahrenheit, 130 psi absolute in an oxidative coupling reactor with the groundbreaking OCM catalyst. The next step takes this effluent and puts it into a compressor, which then the compressed material is put into a treatment reactor with natural gases, and this reactor produces water as a waste material, carbon dioxide as a material to be used later in a methane recycling process, and the treated processed gas that is then put into a demethanizer. This demethanizer produces carbon monoxide and methane, which goes back into the methane recycling process to be talked about later, and carbon compounds of length 2 or greater. These compounds are put into a deethanizer, which separates the 2 carbon chains and the 3 carbon chains. The 3 carbon chains and greater are later sold as other products for other purposes, but these 2 carbon chains, the acetylene, ethylene, and ethane, are put into a hydrogenation chamber with hydrogen gas, which produces ethylene and ethane. These are then put into a carbon-2 splitter, which produces ethylene at a 99.96 weight percent product, which is why this process is so efficient. The ethane, which is removed from the splitter, is put back into the first step, the oxidative coupling reaction, as a new reactant. Earlier in the process flow diagram, the carbon dioxide, carbon monoxide, and methane are put into a methanizer with hydrogen gas, which removes water as a waste and produces methane as a reactant for the first oxidative coupling reaction.
The key unit operation is the oxidative coupling stage of the process. This is where other companies have failed in trying to create a commercially viable OCM process. While other catalysts are viable in terms of conversion and selectivity, they operate at temperatures that are very high and only last for several months, making them not commercially viable to use in the OCM process. What Siluria created was an automated screening process that allowed them to create and screen over 70,000 catalysts in only a few years, finally arriving at a proprietary nanowire catalyst. In this stage, their catalyst performs at temperatures several hundreds of degrees lower than other catalysts and can work for years on end, making the overall OCM process a much more viable process.